personality-wise, in some ways, I'm almost like a liberal arts student whose parents wouldn't let him go that way. And so I wandered into engineering school, got okay at it, wanted to do design, graduated during an economic downturn, and had to take whatever job I could get. So I was designing tools, which was kind of fun, and doing lots of process engineering. Did that for like 15 years. Thought it was maybe the worst thing to happen to a designer to end up being, you know, fixing other people's problems. But the cool thing about it is, you know, when you're walking along behind the parade, you really get good at scooping poop. And so all the other little mistakes, that's scooping poop, baby. You know, you got the elephant poop and the goats and the horses. And a lot of times manufacturing engineering is like that. You know, stuff gets designed and it really is just, you wonder how we're ever going to build it. And you look at it and we spend a lot of time just kind of modifying everything and trying to change our machines and processes and have people stand on their heads so we can go ahead and assemble this product that was supposed to be so easy to assemble. Well, let me get this up where I can see you guys again. That's way better. Okay, good. So I spent 15 years doing that and finally had a chance to move into a design job, grabbed for it right around the turn of the century. And I've been doing that for 20 plus years now. And so that's been kind of fun. For about 8 or 9 years, I was working for huge companies. And then during another bit of a downturn around 08, 09, I found myself on the outside looking in and started consulting. And everybody who'd fired everybody still needed to get work done. So they thought they'd rather rent engineers. So that was what I've been doing for the last, we're going on 13 years. And here's some of the things that I've seen, and what I figured I'd do is kind of walk you through some of the stories that I've seen. I had to comb through them to make sure that I wouldn't be giving away anybody's proprietary data or anything that wasn't already public information. So without further delay, I'll tell you about a little thing that happened during the pandemic. And a couple of you know about this situation. Well, I got a call from one of
Rick,
my—
I wonder, there's on the top of your screen, there's like these pens. Do you mean to have that there? We can see that.
Well, I can't really get rid of them except temporarily.
Okay.
But here's what happened. So I got a call. I got a call from one of my favorite regulatory people, and I've got a lot of them, so I don't want to single Rob out, but
Go ahead.
So he calls and he says he's got a client that he's working for, and they're having trouble, and they designed this really cool thing, and I can't tell you what it is yet, but it was a really, really cool thing, and it had these plastic parts, and the reply that they were getting back for almost every single plastic part was no quote. In other words, no, we can't, we're not going to give you a price for this because we can't build this. And they were getting a whole lot of that. And so the question was, could I get involved? And so of course there's always some money involved, so I always can get involved. And so I was looking at it and took a look at it, and pretty soon I found out that it was one of the more basic and easy to explain kinds of things that we run into. And what it was, whoops, got to navigate a little bit there, don't I? It was this. It was something as simple as the draft on a part. If you were going to make a cup and you were going to try and make it in an injection molding machine, and 3/4 of you guys already know this, but if you were going to try and do it, you wouldn't want to have these straight sides, because if you did, you can imagine the metal mold is going in like this, and trying to get that thing out of there. I mean, even if the plastic didn't shrink onto the mold and give you a terrible time, you'd never be able to get the parts out of the mold. And so what everybody does, if anybody has a molded plastic cup, unless they got really, really clever in their ways to do this with a more complicated mold, but they had a mold with a surface like this. And that makes it really easy to just fall out of the mold. And then the top part that's making your inside is making it like this. And so you separate, the top part of the mold goes this way and the bottom part of the mold goes this way. And this little guy drops out, and it's terribly easy. And this is really, really easy to explain. What we started running into, though, we had some more complicated situations where we were looking at, if you're starting to look at this, some of you will go, oh, well, you just have to do this. And we understand that we're changing an angle here, we're doing something here, something resultant something there. There's even going to be some things going on down in here, real subtle changes, but you notice you still get pretty much the same thing, but it's just a few little subtle changes. Now their complication was they had layer after layer after layer of parts. So they had part, then they had another part that had to fit in another part, then another part that had to fit in another part. So they had all this stuff going on. And the problem was that by the time you started putting these great little angles in, by the time you got to this one at the top, everything changed. So we did have to do a lot of subtle little designs, and it's all geometry. And even though calculus is still pretty opaque to me, the geometry and trigonometry and all that stuff, well, that's just what I did. Algebra and all those kind of fun things. And if you have those tools, this stuff becomes a snap. And if you have 3D technology, it actually gets fun. We used to have all this stuff to do. So these are the kind of things. This is the simple explanation for what these guys are running into. Well, just what I'd like to do is just take a quick walk through some of the disciplines that you all are involved in and how design for manufacturability looks from your view.
Let me ask you, Rick, you started by saying no quote. No one would give a quote to work on what you just showed us as being a relatively simple thing?
Well, the parts, they had a bunch of parts which maybe were a foot long, and the framework might look something like this. And they all had to snap together, latch together, little spring latches and hinges and sort of things like that. And they had all this stuff going on. And the individual parts, well, cooperate with me. There we go. The individual parts all had these straight sides everywhere. They just, you couldn't, if this was like the cross section of a piece that was going along like this.
Is your point that had they made the change that you show on the right, they would have gotten quotes?
Yes, and actually we did make those changes and they did get quotes.
Oh, okay. I didn't catch that entirely. Now I understand. It was a simple fix if they understood.
This is why as many of you as you want, keep your mics on unless you got a dog barking in the background. And then I'll want to meet your dog, and then I'll get all completely lost track of what I'm thinking about. But it was tiny little changes like this. And you'd be amazed at sometimes it can be a change of material, sometimes it can be, but you can imagine if you had a piece that had to snap into, let's say this is the design, and you had a piece that had to snap into this piece. And then you had another piece that had to snap into this piece. And you can sort of imagine a little Russian nesting doll thing going on. And you had to change this one. Well, it wouldn't fit the one that has to snap into it anymore. And then the other one would be even worse. And by the time you got to the fourth layer of piece of the latch or the thing you stick over it all, now everything's completely gone. It's like the telephone game where you whisper something in someone's ear, but you don't quite get it right. And then the next guy whispered is in the next guy's ear. Then he whispers is in her ear. And they all get it wrong. And by the time you're done, God knows what you're going to end up with.
All right, take us through that door.
This door is into the weird door of how things go on. And there's one kind of thing. You get out into a manufacturing line, and it almost looks like somebody got up in the morning and decided they were going to completely ruin things. But nobody does. Everybody gets up in the morning and they try and go, I think I'm going to try and make the world a better place. I think I'm going to try and make it all work. I think it's, I want to make a contribution. Everybody wants to be the hero, and everybody should be. However, sometimes things don't go right, and sometimes the effort put into making a design. Elon Musk remarked one time that most of the effort put into one of his rockets was in manufacturing. And I caught this on LinkedIn, and it was a big thing, and everybody's arguing, and all the designers like me are going, "Oh no, it's really the design." And the answer is it's both, but he's absolutely right. The art of making making things work is actually all in the manufacturing. And so if you're on the design end of things, it gives you an obligation, not just to make things work, but to make them likely to work, not just to make sure that they can be assembled, but to make them likely to be assembled. Now you're thinking, now you're not just thinking in physics, you're thinking in statistics, and you're thinking in human beings and how do they work. For quality control, this is a very, very simple drawing. And for quality control, if your drawings are laid out in such a way that anything's unclear, that you've got dimensions that can't be measured in the real universe, and you've got things that are and actually I would have thought of it if I could have, but I missed it. We actually had a pacemaker can. It was actually a neurostimulator, but what we had was they very cleverly, there we go, and okay, it's nice and flat. So the way it was laid out in the drawing is a radius, and a radius, and a little one here, big one here. And again, this is all over in the area of drawings and how being able to communicate at the beginning helps people at the end. Well, it just so happened that the guy who was installing our optical gauges was hanging out with us and installing something new. And we were showing him this and how we couldn't measure it twice and get the same exact reading every single time. And we couldn't. Everything was different every time you measured it. He looked at it and he scratched his head and he said, well, of course it's not going to work. You're going to get a different measurement every time. And we said, why in the world is that? Because in our world of linear thinking, you just kind of want to go, well, if you measure it, of course you'll get the measurement. He said, because it's impossible. Because whether you're using touch or optical, you're getting a series of readings like this, and no matter how close they get, they're going to be a little different every time. They're going to give you a different result, a different calculation. He said, you have to go at least 2/3 around a circle to get something that's consistent. I said, no way. He said, way. So I said, show me the math. And he sent it to me. The man was right. But the guy who's doing the drawing on one side, if this radius was important here, and he's designing this part, and he just labels it like a radius. He says, this is the radius of 0.060 inches or something like that. It's useless. No one can measure it. And this affects quality. And if you're not designing well, it affects quality control. Because quality control basically had to resort to making a bunch of these cans, test fitting them together, and pronouncing it okay.
Jorg and Andre had an interesting side conversation in the chat. Would you share with the class?
Well, yeah. So not only, well, I really had two comments. One was obviously, you have all these drafts and everything else that make things fit and pull out of the tool and so forth. But all those things have tolerances on top of that. So when you have multiple tolerance stack ups and things, that's when you start having, to Rick's point, things start stacking up and where you can really have problems. The other comment I made, and probably maybe some people will argue with me, but I think 3D printing in general has hurt the design for manufacturability in many cases, because you can pretty much just print anything, right? And so when you print anything and go, yeah, that looks good, it works, I can put it together with something else, that's a long way from having a part that's manufacturable, because they don't draft. That's why we, for example, in our design processes, even when we're 3D printing, we're putting in draft and everything else, because we don't want to lose the manufacturability aspect just because we're doing 3D printing.
And Jorg, we come across that all the time with clients. In fact, the biggest problem that we have now is they'll go to a design firm, spend a lot of money with an industrial design group, come up with this unbelievably beautiful enclosure for an electronic product. Then they'll come to us and say, okay, we want to quote on 5,000 of these. And the injection mold is just impossible to make because they've got, cutouts in the wrong place and so forth. So the 3D printing of prototypes really gives unrealizable expectations to customers. And
Correct.
That has hurt us. It has hurt us.
Yeah, and that's one of the things. If you've been doing this for a while, I'm going to give away my age. When I started learning to draft in 10th grade, okay, for years and years, the standard of drawings was going to be pencil and maybe ink. And our idea of automating an assembly was making a Xerox copy of it on transparent paper and then taping it right next to it. That's what we did. That was cut and paste.
Yep.
And we did that for years and years and years. And I sent myself back off to school to learn CAD. And then I joined a company where they were going to teach me what I didn't know. And but that was it. That was our standard. And there was a lot of stuff that was so hard to do if you didn't have CAD that it wasn't worth designing. But and so we had to use a lot of imagination back when there was pencil. But you also have to do that. You also have to do that, as you guys just pointed out, when you're working with something that you can make impossible things and you can design impossible things. And the big issue is with us designers, is that we design impossible things.
Yeah, even in packaging, I get weird things where I might have heat or radiation exposure or something, and that changes my tolerances and fits. And I have to account for that. And you're not going to get that in a 3D printed item either. So makes it fun.
Not only that, but skill levels vary among CAD designers. I remember one time when, for one reason, and I did it half for fun, but also because we had an application, but I actually made a CAD design of a Ziploc bag with the flexibility because we needed to portray something photographically. And so it's got open and closed and various things like that. But even when you've got all the skill that you need, if you're not pretty much seeing in 4 or 5 dimensions at once, you're gonna miss this stuff. So what does it look like to
Luke, you had something to add?
Oh, sorry.
Yeah, it's in the chat. Right now we're doing a process failure mode and effect analysis on the process of building a product together. And it has 7 parts that have to be glued together. And it's almost impossible to validate because the work instruction says you must have the right amount of glue and it mustn't go over the edge, and you must have enough glue that it sticks, but not too much that it will get in the way. And the only way you can validate that is by qualifying the people who are doing it. So you teach them how to glue, and
well, or automating it. You know, you could build a fixture and have a 3D device.
Yeah, but not for 200
down,
products a year.
Yeah, but it's difficult. That's expensive. Yeah, absolutely.
Nelly?
Yeah.
So I actually have a client, and I won't name drop or anything, but they're doing 3D printing, and they're like, well, to design and mold right now, it's just too costly. We're going to go to clinical trials with 3D printing, and I'm all, but you haven't even considered it. So how are you knowing if you can manufacture for the quantities you might need? But they don't want to hear that because it's like they've successfully gotten to a point where, well, we can do the 510K with this. And I'm like, well, if you do molding, don't you have to do like an update, because that's a major design change from 3D printing to molds? And so I totally understand what you guys are talking about, designing for manufacturability, because when I question them on processes, they're always like, well, this works right now. And I'm like, yeah, but guys, have you worked in a manufacturing environment? Do you know what that's going to be? I mean, I worked for a company that the cost of manufacturing the device was over. By the time they shipped the device, we weren't making money, and we hadn't even paid sales commission yet. And it's like, you got to consider those things, the steps and all that.
Bobby?
If they make a change to the design that's significant enough, they'll have to redo their whole clinical study too.
Yeah, exactly.
They always ask, what version did you do your clinical study with? And then look for reasons why you need to repeat it.
You guys just walked me right into the next section.
We were glad to help you there, Rick.
You always do. I try and pitch well, and boy, you guys catch well.
Yeah, I actually have a client who is shipping product with 3D printed components in it, which I told them, wow, that's really not good. So now they're in a redesign, and we're going to design all those parts out of 3D printing, because
I don't, this isn't my specialty. So are you suggesting that 3D printing is either has too much tolerance, too much variance, and can't be relied upon? Or are we saying, in the spirit of today's talk about for manufacturability, are 3D printers being used to mass produce anything, or is it more like a design tool?
Well, I see it more as a design tool. There are certainly cases where 3D printed parts are final parts, but again, they have to be validated. They have to be proven to have repeatability and all those things. And most 3D printing systems aren't really designed for that. So I think it is possible, of course, and there are situations, I know in aerospace, where they do certain complex duct work, but all that is, again, it's very much controlled. Each part is tagged and labeled and validated. So it's not in a medical device. I would, as a general rule, I'm sure there are exceptions. Your standard 3D plastic parts, for example, that are 3D printed are just problematic.
Now you guys are 2 sections ahead of me. So
Sorry.
Well, just
You're
a quick
anticipating
note.
us, Rick. That's all.
I'm going to shut up. I'm going to shut up.
Y'all are doing great.
For individualized products, I think there is a case to be made, like Invisalign and products like that, where they're actually custom made. In that case, I think 3D printing actually makes a lot more sense than the conventional molding. So probably a few exceptions, but there are some cases where 3D printing makes more sense.
Yeah, that happened to me. I've got a client that's their medical device is a 3D printed item, but it's individualized for people. But they're having me do their packaging, but I couldn't find any of their biocompatibility and other stuff they were supposed to have to go with it. And I'm going, why are you working on packaging right now?
Yeah, well, also 3D printed parts have other issues with sterilization. They're not happy with, irradiation or other types of processes. So you have to know there's a whole world of understanding that has to exist there.
Yes.
And the interesting thing about that is that Luke was getting into this. When you're doing FMEAs, the whole process of evaluating how a process is going to go is going to depend on what that is. In other words, if we're really used to talking about how we're going to drill or turn down some metal or something like that, or even injection molding, and now we're talking about another process, which is additive manufacturing. That's our old 3D, and we're talking about that. That's going to have some things, and the whole process of, I've been brought in. I was brought in for a few weeks one time because an automotive accessory company was trying to put an FMEA together, and they had their 17 most technically expensive people in a room for like hours and hours every day, and it was miserable. It was like torches. When this is going to end? And so what I did is I came in and I'd pop in and I'd ask them about 1 million questions, and then I'd go home and do that much of the FMEA, show up on Thursday, do it again. In 3 weeks, we're done. It was an hour every day. No, it was an hour twice a week, and we got it done. But the thing is, if you're not doing this kind of evaluation, you can easily run into something or something similar to it. You can easily run into a situation. And how does design for manufacturability affect that? All kinds of things, even the ability to be able to maintain relationships between your parts and understand what's going to affect something else, to be able to say, well, okay, let's experiment with something else. And the ability to do stack-up analysis, the ability to do these things really easily. If doing a stack-up analysis is hard and time-consuming, if doing an FMEA or risk analysis is hard and time-consuming, it is a fantastic time to get help at doing that. But you guys actually now are getting 3 sections ahead. So I'll just throw this at you too. For electric, no, that's what you get. If I had a crowd of high schoolers, they'd still be texting each other. Anyway, so it's like for electrical design, we had this is the very first thing that I ever designed, and it was an old turn of the century internal power source with capacitors and batteries and the whole 9 yards for a left ventricular assist device, basically to keep somebody alive till they could get a heart, but at the same time they could run around, take showers, things like that. Well, so we had this going, and about the second time, and here are the flex circuits that we were designing into it, and there's a solid circuit that plugs into the flex circuits. Here are the caps, and the second I saw the first version, and of course they tried to fold it around, and it was sort of like one of these really cool puzzles by the time they got it all done. And then I looked at that and I said, what are those things? And those are jumpers. Well, when we folded it together, nothing would exactly, we had a few things that interfered with each other, so we had to move the capacitor over, and the jumpers are to make sure that those things stay live. And so instead of looking like this, it looked like this, with a couple of solder points over here because I had to move it. So I talked to the electrical guy and I said, could I do this in CAD for you? And he said, no, we'll totally get it right this time. We'll totally get it right this time. And so the second time, there were more jumpers and things like that. The third time, they let me go ahead and do it. And a lot of times, design for manufacturability isn't just the mechanical stuff. It's everybody that you affect. How's it going to affect packaging? How's it going to affect your electrical people? You're going to have design for manufacturability can also affect how things are going to, how your seals are going to work, how everything's going to go together. And if I do get a chance, I won't even dwell on these, but if I do get a chance, I'm going to bring something that if you were alive and watching the news in 1981, the entire world saw this disaster, but they didn't see the design for manufacturing disaster embedded in it that caused the entire thing. Nobody has seen it. So this is, when it comes to your manufacturing floor, if you are designing something so that the build is logical, so that it can only go together one way, the Japanese call that pokio, so that it makes sense to put it together a certain way. It takes a bit of extra thought in the beginning sometimes, or so that it won't go together unless it correctly goes together, also pokio. If you can do that, you can avoid things just getting stopped and destroyed and reworked at various ends of the production line. You can keep all those kind of things from happening to you.
Michelle?
Oh, go ahead.
I'm having a little bit of PTSD here. My first recall ever was a combination of about every single thing that you've talked about, short of 3D printing, because it wasn't around then.
Oh my God, we're not done.
But yeah, it was like the parts were designed and the stacking tolerances were loose. So, and they were supposed to be press fit parts that couldn't stay together. The drawing allowed flash at the mating surfaces. Then you take those two parts that are supposed to fit together and you send them to the assembly line, and their solution, rather than fix the mating surfaces and the flash, was to put a fixture on the manufacturing line to check if the fit had locked or not.
Yep.
And then, you know, fast forward, they're doing they're trying to validate the mold in a new press. It's supposed to be a validation run of 8,000 parts, and they overran it by 28,000 to fill inventory and release them to build before the validation was complete. The measurements were complete. And then I have 28,000 resuscitators that fall apart in the field. And then somebody in planning that had started this whole thing growing came into my office one day, and I was super stressed out, and I probably snapped at her, and she's like, you know, you used to be really easy to work with, Michelle. So anyways, I mean, all these things are just very real. And if you start the process bad, the ball just keeps rolling down into manufacturing until you're pooping and scooping from the minute the resin came in the door to when it's out in the field.
Yep. And anybody is, let me see, I'm just kind of looking over everybody. I can see everybody pretty much. Ed and Michael got your cameras off, but I see everybody. We've all been doing this for a little while. And it is, so for any, you know, I can, if the PTSD is too bad, I recommend betterhelp.com. They're very good. And for some of it, especially if you really care about what you're doing, and I don't see anyone here today who doesn't. So it's actually seeing some of this go on. Michelle's joking about PTSD, but seeing some of this goes on is actually mentally traumatic. It's part of the toughness that you have to do with what we do is just absorb it, fix it, move on, and understand that we're working with human beings who if I don't make it likely that they're going to do it the right way, they probably may not.
John Tuckwell has something to add.
No, I was just going to ask Michelle if this is when she took up vodka.
Tequila.
She's a tequila lady.
Oh, sorry, tequila.
Yeah.
I didn't realize
some of these parts were made in Mexico, so there was a lot of time spent in the bar after work.
Rick, maybe before your next presentation, we can do a mailing of sedatives.
Yeah, it's, you know, every time I go through one of these things, it's like the psilocybin commercials look better and better and better. And so I'm just, yeah, I don't know.
Chris, you have something you wanted to add? You are on mute, kind of, but it doesn't think that you are.
Weird.
That's weird.
Chris Kelly has a design for manufacturability issue. Continue, Rick, until we figure it out.
Well, I had something I wanted to add because I have had, I've worked in companies where they get parts in that don't meet the drawings and they decide to use as is, and then it causes problems in manufacturing, but they don't relate it back to the use as is. And then they have problems out in the field because they had to use as is. So I had to, I know in one company, I had to link all of those things together so they would recognize you don't use as is when something's out of spec.
This is all of these things that we're talking about are things that happen because design for manufacturability was not done. And there's a couple of ranges. There is electronic convenience, design for manufacturability, and there is, and I don't have anything from space, but there's NASA. Okay, with NASA, it's got to be perfect, triple redundant, and everything else because you're a bazillion miles out in space, and if something breaks, you don't want a bad version of Apollo 13 when it comes back. But you can, you know, but you can be a little less NASA if you're designing a mouse. But if you do it badly enough, no one's ever going to buy that thing, and word will get out. The marketing guys need to know when they're asking you to do something that can't be done. And sometimes with the marketing people, you need to say, hold on a second. What you're saying is physically impossible. So give me an hour to go off and figure out how to do the physically impossible, and I'll get right back to you and we can resume our conversation. But there's no point in continuing it here because you've completely lost me. However, it's also nice if you know how things are going to go together ahead of time. You can also make these great pictures of them that they can put in some of their things. Purchasing, we looked at a little bit. And when you're looking at purchasing, it's just like, well, okay, so what's wrong with purchasing? You just sling it over the wall and the purchasing guy gets it. Well, what if the stuff you sling over the wall can't be built? What if it's unlikely to ever be built well? What if you put a little more thought into it, you could have made it cost half as much, which means if it's a medical device, maybe more people will be able to get it in their insurance plans. What if you have something that can be made so inexpensive that it can be put on a credit card? I know a guy in San Antonio who's doing it with the artificial hand. I've consulted with him for free because I love what he's doing. And he's doing one for a fraction of the cost of an artificial hand, and we're talking heat sensors and everything else. He's got it built in, and he's almost got it ready to go. And what if you can do something? What if $10,000 of thought on the beginning end can save you $700 million of thought on the back end, and something that only could have gone to the very, very rich can now be afforded by anybody and can go on anyone's insurance plan. And that is like the goal. I work on as many things as I possibly can that make sure that that the thought goes into it so that things can get to everybody. I know we can't afford to give everybody the most expensive thing in the world, but what if we can put the thought into it to make as many things as possible affordable for everybody, even if they drive a bus, even if they dig holes for a living, even if they don't do highly technical things like all of us do. But if you've seen production delays, you've seen things fall short, you've seen the manufacturing guys coming back saying we can't build this. What does that do to production schedules? If you want a reliable production schedule, put enough thought in beforehand into the design. Don't just be thinking in tolerances, be thinking in statistics. There are a lot of skills that are going to go into making sure that a lot of these things happen. But I'm going to throw a specific out that doesn't have anything to do with medical devices, and it doesn't have any, and you'll be going, how in the world is Rick going to stretch this out from this and turn it into a manufacturability issue? And of course, I'm going to talk about the Hyatt Regency walkway collapse. Here's what I'm not going to cover. I'm not going to cover the hours that we talked about it in civil engineering, going through the mechanics of actually how it collapsed. I'm not going to do it. I'm going to show you some pictures, no dead bodies, but it was a disaster. You can see here, there was a sky bridge. Here, there was a sky bridge held up by cool cables like this, basically big steel bars. Okay, now, spoiler alert, the steel bars were strong enough. Other spoiler alert, that even though they did 1,000 things wrong, the design was strong enough. So how'd this happen? How'd they fall down during a dance and kill hundreds of people and produce the second biggest life loss disaster in the United States in 1981, which we all got analyzed like crazy in civil engineering in 1982 and 1983.
How many people died?
183 keeps sticking in my mind, but a number over 200 does. So you have to get to get more people than that dying from a structural collapse, you have to go to 9/11.
Wow.
So again, no dead bodies, but you can imagine, right? This one stayed up. It was just a disaster. This is when it was all working. You can see these huge steel cables hanging down. Here's somebody walking across. It was perfectly secure. Here was another one. So we have, starting from the bottom, 1, 2, and there's the third one. And I'm also not going to get into all of the different things they did wrong. They had design changes going around as handwritten notes, phone calls, word of mouth, no design changes, no verification. Anybody who has probably heard me is, anybody who, we all love to criticize bureaucracy. We all love to criticize paperwork. If we could just cut the red tape, everything would be fine. Everything would be great. Well, if you're going to cut the red tape, you better just get ready to be gone. Because the guy who was the head engineer designing this stuff spent the rest of his life, no one went to prison, but he spent the rest of his life touring the United States, trying to warn people about all of the horrible practices that went into this. So with, again, avoiding a bunch of detail, because we're going to get to the weird part that nobody saw. When they built this together, it was supposed to be a support that went all the way to the bottom. And again, real strong. What happened? Well, this is all threaded. This is all threaded material before it's covered up and looks all smooth. But it's all like a gigantic all thread, the biggest all thread you ever saw, right? And these are all secured by nuts, which were also strong enough, into plates, which were also strong enough. They looked like they were probably designed with a safety factor of 2 or for 3, but oh well. Anyway, and so they went all the way up here, and somebody said, do you know how long it's going to take? Because nuts were going to have to go here. They said, do you know how long we're going to be screwing to get these nuts screwed all the way up to here for like 20 different supports? It's going to take forever. It's going to slow the project down. We're going to lose efficiency. And I'm all for efficiency. But through a series of deviations from plan, they started doing it like this. They had one that was this long and one that was this long. And I could look at the last Aggie bonfire, and I am a proud Aggie, I suppose, but instead of having a single center pole on the fire, they didn't have a long enough tree, so they had 2, and they spliced it together. Where did they splice it together? Exactly in the weakest point of a supporting column, the center. And you'll just have to take my words on that if you didn't go through all the mechanical engineering classes. And here's the close-up on what they did, and I'm just going to kind of zip right through it if I can. This was to plan. This was the way they did it. Now it was much more convenient. It was much more quick. They got to use shorter pieces, and it put exactly twice the strain on these welded box beams. Anyway, again, without getting into all that, this is what happened. It was a series of gunshot-like pops, and then everybody was dead. And here's a I just grabbed this from a reference manual. This is a giant piece of all thread. Again, this diagram, which you've seen. So I was watching with my wife, we watched Engineering Disasters, poor thing, and she likes it too. And so we watched that while we eat lunch at our house where I work. And I suddenly realized what had gone on. Now, all of these things happened. There was a series, you could write a book, and people have, on all of the different wrong practices that resulted in this. But remember this thing today, we're on design for manufacturability. So what do you suppose a guy like me was thinking? I was looking at it and going, okay, so he designs this brilliant design, the engineering numbers work, and they do. And so he's got a big, long piece of all thread, huge piece of all thread, and they've got all this going on. And here's what he's not thinking. He's not thinking, I bet everybody will really be excited about spending an extra 2 days having lots of crews of people screwing those extra nuts onto the all thread. So you're not thinking about how can it be built? If it can be built, what if it's built wrong? We're used to thinking about that. What we don't think about is human beings and statistics. We don't think about how is it likely to be built? What do we think is going to happen if we throw an idea out here that all relies on people wanting to do this? What do we think is going to happen? And when you're designing a product, when you're looking at somebody's thing that they're just about to put really all of their fund money into, and they're going to dump it out onto the market, and they're going to put it into research, and it's going to cost a fortune if they have to redesign it. Doesn't it make sense to think about how it's going to be used, not by the people, but by the people who assemble it? So let's see, got one more illustration. These illustrations are pretty much all from US patents of one particular thing. So I was called in to evaluate a little torque wrench, and they said, well, we've got this thing, it's great. We just want to do design for manufacturability assessment on it. And I took it apart, and the DFM report was not going to look great. But then I took it home and I found out it didn't work. So I ended up redesigning the thing. And in redesigning it, had to use all of these principles. For a few dollars, instead of $500, I'll give you an idea of what we're replacing. A breakover torque wrench. And I told them flat out, 20% chance we won't succeed, we'll have nothing. You know, you pay me all this money, we won't get anything. But they were desperate. And we figured it out, or I figured it out. And my name's really never on a patent, almost by rule, because I work for geniuses and I figure out how to make their ideas happen. So I'm sort of holding hands on one hand, genius. On another hand, manufacturing, production, fabrication guys. And I speak both languages. I can speak PhD and I can speak 8th grade, not a problem. And I'll tell you a secret, some of these 8th graders are a whole lot smarter in many ways than some of the PhD people. So figured out a way to do it. But while we're doing this, a lot of people would go, well, what's the best theoretical way to do it? But I started with the processes that we could afford to make this thing for a few dollars. What could we afford to use? That narrowed it way down. What did that do? That changed the tolerances that we're going to be able to use to make it. Oh, okay. Well, that's going to change a lot of things. But what it did, it sped up the process, which took months, to go through several designs and make sure that we could reproduce something like this. It took some analysis, and I farmed some of it out. And by the way, I called Joe, and he recommended a metallurgist she was fantastic. She not only knew the different metals that were more likely to do it, and we picked an odd stainless steel, but she also, now this isn't the design we use, this is just one of the, some of the finite element analysis, but she not only knew what had been invented, but she knew how likely it was that we'd be able to get some. She knew what was available. She had an idea of what the market was like. And so we didn't waste our time on unobtainium. Ended up with something really simple. Still didn't have enough time. Called a friend of mine. He designed the plastic housing because I just didn't have time. I was doing the experiments on this, more stuff from the patent drawing. And again, my name's on like 2 or 3 patents in the world because I usually don't have to do anything except figure out how to make things work. And if you're into DFM and you want to have your names on patents, you're going to be sad all your life. You're going to really be miserable because the geniuses that are hiring you have already figured it out. They already know what they're doing. They're just going, we have no idea how to make 2 of these things. We've got 1 and it works fantastic, but we don't know how to make 20,000 of these things. So you can end up with something very pretty and very simple. But you can start out, if I had to, and actually contractually I can't, but if I had to show you the reams and reams of experiments and tests and things like that, and different metals we tried and titaniums we went through and everything else, if I had to do that and try and show you what we were doing, it would take forever. And we would be and we'd be here for, well, it took me months just to do all that stuff. I hired all my children to help me do the experiments, and I hired another child to help me do the graphic design for something else, and it just, every resource I had.
It's a good thing you're so virile to have that much help.
Well, I was virile enough to have 3. And
Eddie Capabianca, you had something you wanted to ask or add?
Hey, Rick. Yeah, that bit of the presentation about the bridge was really interesting. I do vaguely remember that. If you wanted a less lethal bridge example, are you familiar with over here in the UK we have what's called the wobbly bridge?
Is it like a version of Galloping Gertie?
It's a beautiful looking bridge that crosses the Thames.
Is it still up?
They didn't. What's that?
Is it still up?
Oh, yeah. And it's still called the wobbly bridge, even though it doesn't wobble anymore. They built this thing. It looked beautiful until they allowed human beings to walk across it.
Yes.
And you got enough people walking
across. I saw a video
about
it. Yeah.
And they didn't figure that everyone was going to end up walking at the same pace.
Yes.
And so then they had to double the price of the bridge to put in dampeners. So it doesn't wobble anymore, but it got the name. And
so they're still using those huge weights that they hung from underneath?
I think so, yeah.
Oh my God. But it worked.
Anyway, with respect to, but bringing it into the medical device world, our own company with our catheter, I joined the company, a lot of it had already been designed and then getting redesigned. We're into a 2nd generation, but I'm a little frustrated because the design engineers that we had been working with, we're not working with them anymore. When they did their redesign, they didn't think through a lot of other simple fixes that would allow us to, I'll look at it as a positive. We've got a lot of cost we can take out of our device because our pusher rod is still a tube, which is a good 2 feet long, which is quite expensive to have a tube that is completely unnecessary, that is as thin as a pusher rod. So, they hadn't gone through that holistic, okay, if we're doing this, all the stuff you were just describing. So it is important to look at the whole and figure out, well, what does this mean? And what does that mean for that? So
I used to hate cost reductions because I thought they were so materialistic. And I thought it was just somebody else trying to grub a little more money, to send off to somebody. When I was young, we all start out this way, right?
Yeah.
And I thought, and it seemed like the lowest form of science until I realized that all the stuff we make, somebody has to pay for the damn thing. They really do. And you're going like, and not everybody can, because I got a lot of friends who can't pay for the stuff that I can. And I got friends, I could never afford what they're doing. And it's like, when it comes to medical stuff, what's the answer? Well, let's just invent the most expensive thing we can and then buy one for everybody. And that just becomes untenable. So instead, can we make it better? Can we make it less expensive and just as good? And if you've ever heard of the Jaipur knee out of India, if you haven't, worth reading, really worth reading. an engineer in India came up with a non-powered knee that works just about as well as our most advanced stuff. And they had India's got a gigantic population, and they've got industrial and farm accidents that happen and things like that. And people whose lives are transformed into near uselessness by losing one or more legs. And this changes it.
So I know we're getting close to the end of the call. Before we end it, I just want to put in a design for manufacturability plug or design for serviceability plug for all those poor service engineers out there that have to try to figure out how to repair capital equipment. My experience is that we had a replaceable battery in a product. We put it on the bottom of the fourth circuit board in the bottom of a stack. Our people were not very happy with. So please consider serviceability. The other thing is that Rick is presenting this really well. Typically, the design for X will conflict. So something that makes it serviceable may not make it as manufacturable. And so this is all a very complex thing to try and balance all of those needs. And kudos to Rick. I'm glad you're out there doing that for us.
It is. The thing I get is, and there was another question too, I thought, but
Jose, yes.
I work for geniuses. I work for people who've come up with unbelievable ideas. The whole reason that all those, if you ever saw a show called The 21st Century by Union Carbide that came out in the 70s or whenever, 60s, and as a kid, I would watch it and it would talk about all these ways the world is going to be a huge disaster and we're all going to be dead and we won't be able to support the population and there won't be food or anything like that. And I think the UN's latest statistics on food availability have just been incredible in terms of over the last few decades, the availability of food for people. Is there more to do? Absolutely. But the people that I work for it's so exciting when I'm just walking along or out on my bike and stuff like that, thinking about it. The people that I work for are actually changing the world. And in everything from energy to animal husbandry, not just medical devices, to all kinds of things. And they're making these incredible changes. And it's all that innovation. And it's almost, I've got almost a religious adoration of all of that stuff. Because it's really just, they're freaking amazing. And I get to work for them, which is why my name is usually not on patents. Only when they really have trouble, or they really get generous with their patents, is my name over there. But
Jose?
There it is.
Yeah. Now, all I was going to say is, so I know I'm preaching to the choir, but I like the saying that you don't pay your plumber to bang your pipes, you pay them to know which pipes to bang. And, I think that's one of the things that I see a lot of entrepreneurs sometimes not realize is that you can't skimp on like really experienced engineers and designers, and people have kind of got the scar tissue to know all the various mistakes that you can make. I think you gave a great set of examples around the mechanical ones. I think, we tell clients all the time too, when they're developing products, we go, look, you're really developing a couple of different products, because for every device that you develop, you're also going to have to develop test fixtures for them, right? And so on the electronics front is knowing how to do your design for test as well, right? So making sure that you've got the right kind of test points in place and that you're thinking about in manufacturing, how's this thing going to be, tested so that that the thing going out the door actually passes everything. So just like in mechanical and electronics and software, you just have to always be thinking about these various things, which without experience, you don't realize it, right? You have to get bit a couple of times before you realize how important some of these things are. So thanks for sharing all this.
It's tremendously fun. I never thought work would be this cool.
Rick, this was a very well-attended and engaging conversation, a lot of participation. So thank you for those thoughts. And I hope folks who have those kinds of needs are keeping you in mind and reaching out to you. Folks, I'm not sure who our presenter is for next week, but I have a couple of folks who are potentially going to be meeting with us. And a friend of mine from business school is in corporate venture investing with Cleveland Clinic. He's going to be my guest at the end of the month. So I think that'll be a really interesting one for folks. It is just shy of 10 weeks for our get together in San Diego. If you're thinking about it, let me know. And see you next week. You know where to find me. Thanks, everyone.
Thanks.
Bye for now.
Thank you. Bye.
Bye-bye.